Okay, so this is page 77 and 78 of the notes, and this is classical probability and Venn diagrams. All right, so we have some vocabulary to start with. First off, mutually exclusive and disjoint. These two words mean the same thing. Mutually exclusive and disjoint are the same. Okay, they mean exactly the same. They're synonyms, and what they mean is these are events that cannot occur at the same time. So events that cannot occur at the same time. You cannot take a coin and flip it and get heads and tails on the same coin flip. Sure, you can get heads sometimes and tails sometimes, but on a single flip, you're going to get one or the other. It's impossible to have them both. So if I were to draw a Venn diagram, I would have 50% heads and 50% tails, and notice there's no overlap. All right, so if they're disjoint, there's no overlap. There's no overlap, or no, and I'm going to use this symbol a lot. That's the intersection symbol. So there's no overlap or no that, which is no intersection. All right. So mutually exclusive and disjoint means there's no overlap, there's no intersection. Here's another Venn diagram. You cannot make 100% on the test and make an F on the test at the same time. All right? Not possible. You either get 100% or you get an F, but you can't have them occur at the same time. Let's pretend that the probability of getting an A is 20%, which is what we show here. The probability of getting an F on the test is 10%. All right? Well, notice I can't get an A on the test and an F on the test, so they don't have any overlap. They don't have anything in common. But that only accounts for 30%. But, so 0.10 plus the 0.20, but if I subtract that value from 1 minus the 0.3, I find out that there's about a 70% chance of getting something besides an A or an F. It could be a B, C, D, or D. All right, so this 70% represents the B, C, or D. This is the A, this is the F. And together, the 70 plus 20 plus 10 adds up to one whole. And that's what a Venn diagram looks like. Here, I don't have this boxed in because there is nothing on the outside. It's either heads or it's tails. This happens half, this happens half, and they add them up, that's one whole. Here, I had something besides the A and the F that could happen. That happens 70% of the time. Complementary events, okay? The probability that an event will not occur. Whenever we have a complementary event, I always want you to think 1 minus the probability that they were talking about, okay? And another way to say, what's the probability of not A? Well, 1 minus the probability of A. So looking at our heads up here, the complement of heads would be not heads, all right? Which in this case would be tails. The complement of tails would be not tails, which in this case is heads. All right? Those are those answers. The complement of A would be not A, which would be, I could get a B, C, D, or F. The complement of F is not F, which is going to be A, B, C, or D, absentee, or passing, all right, not failing. All right, please pay very, very careful attention to this. This is one of the more difficult concepts that we'll be talking about today, and this is independent events. Independent events are events that do not rely on each other. If, circle that word if independent, then the intersection or the overlap equals A times B. So if they're independent, the intersection equals A times B, or the overlap equals A times B. Also put a star by this. Mutually exclusive is not the same as independent. They're different. Mutually exclusive is not the same as independent. They are completely different. Also, events cannot be mutually exclusive and independent. All right, events cannot be mutually exclusive and independent. I'm going to say it again. Events cannot be mutually exclusive and independent. And someone's going, but Mr. Spencer, it says unless. You're right. There is a special case, and that's just the probability of 0. And you're like, well, okay, so there's a special case, so they can be. And I'm like, well, yes, mathematically they can be, but I want to go back. Events cannot be mutually exclusive and independent, and here's why. We don't care about the probability of 0. Why? Because it ain't going to happen. We care about things that are going to happen or might happen or could happen or should happen or likely to happen. But if the probability is 0, it ain't going to happen, so it's not of interest. We don't care about those, okay? So, generally speaking, events cannot be mutually exclusive and independent unless a probability is 0. In other words, not really going to happen, or it's not something we're that interested in. So a game requires that you roll a fair 4-sided die. Well, if I'm rolling a 4-sided die, I can get a 1, 2, 3, or 4. Those are my options. I can't get 5 or 6. Just a 1, 2, 3, 4. And to flip a coin. So I can get a heads or tails. The Venn diagram illustrates the probability of getting a heads and rolling a 1, 2, or 3. And so the question is, where did all those probabilities come from? First off, I want to talk to you about the probability of getting a 1, 2, or 3, because this is the 1, 2, or 3. So the probability of a 1, 2, or 3, oh, that's 3 out of 4, or 0.75. And the probability of a heads equals 0.5. Well, typically speaking, when I'm working with Venn diagrams, I like to work with the overlap first. I want to work with the intersection. And please remember, this is the overlap, so this is the intersection. All right? Now, question is, are these independent events? Is flipping a coin and rolling a dice independent? Well, we need to ask ourselves, does one impact the other? Does flipping a coin impact rolling a dice? And the answer is no. I can do one and it won't hurt the other, etc. So if that's the case, I can use my multiplication principle, and this is also known as the multiplication principle, and I should have said that. All right, so that's the multiplication principle. And so I can use that. So the probability of 1, 2, 3 intersect the probability of heads equals the probability of 1, 2, 3 times the probability of heads. So let's see what happens. We know the probability of heads, or 1, 2, 3, is 0.75. And the probability of heads is 0.5. And that equals 0.375. So this is where the intersection happens. So this represents the intersection, or the probability of 1, 2, 3, and heads. That's what that represents. Okay, so we know the intersection part, so let's delve with heads, because the heads is easy. This is the head circle, all right? Well, we said heads had to add up to 0.5. But this whole circle, everything in the circle has to add up to 0.5. So if I take 0.5 and I subtract minus the 0.375, I end up getting 0.125. So that's where that value came from. All right, that's where that value came from. So 0.5 minus the 0.375 equals the 0.125. And that went right there. Over here, right here, well, actually, let's talk about this one more time. This is the probability of getting a 1, 2, or 3, or a heads. This is the probability of getting a heads, but not a 1, 2, 3. So this is essentially going to be heads and 4. Because I got a heads, but I didn't get a 1, 2, or 3, so I must have gotten a 4. Here I have the probability of 1, 2, 3, and so the probability of 1, 2, 3, we said, oh, that's 0.75. And 0.75 minus 0.375, find a room to write this, 0.75 minus the intersection, 0.375, equals 0.375. And that gives me this, because here's my intersection. And everything in this circle that I'm going to do in green, everything right here represents the 1, 2, 3. Okay? All right. So what is this? Well, obviously, this is getting this right here is getting a 1, 2, and 3, but this is heads, so this has to be not heads, which means it is tails. So 1, 2, 3, and tails. So this is this section right here. This one right here is 1, 2, 3, and tails. Well, where did this number come from? Well, if I add up 0.125, 0.375, and 0.375, if I add up all those values, I end up getting 0.875. Well, this has to add up to 1 whole to be a valid probability distribution. So 1 minus the 0.875, once again, that's the sum of this plus this equals 0.125. Okay, so that probability right there is 0.125. Well, if this is heads, that can't be heads, so this must be tails. If this is 1, 2, 3, this number can't be 1, 2, 3, so it must be 4. So that's the probability of getting a tails and a 4. Okay? All right, so we're going to come back to that in just a moment. We're going to come back to the same Venn diagram. And I want to talk about the general addition rule. By the way, you do not have to memorize this formula. I will give this to you, but you do need to know how to use it. This symbol, A union B, the union means or. So A or B equals the probability of A plus B minus its intersection. All right? A plus B minus the intersection. And please remember, the intersection is always the overlap. So let's use that to the probability of getting a 1, 2, or 3, or a heads. All right? So this tells me I'm using the union. All right? So I want the probability of 1, 2, 3 union heads, which equals the probability of a 1, 2, 3 plus the probability of a heads. And I'm just going to abbreviate and go minus the intersection. And we'll talk about the minus part in a second. Well, the probability of a 1, 2, 3, the probability of getting a 1, a 2, or 3 is 0.75. The probability of a heads is 0.5 minus the intersection is 0.375. And now we get back to that 0.875. So my union is there. That's my answer right there. Now the question is, why did you subtract? Well, first off, this plus this is 1.25, and you should immediately go, hey, that's a problem. We cannot have a probability greater than 1. So we have to do something about it. So we are going to need to do something with decreases. In this case, we're going to subtract. So 7.75 plus 0.5 is this. We subtract, and we end up getting 0.875. And you're like, okay, so that works mathematically, but I don't understand. Here's why. This circle is the head circle. And that circle represents 0.5 because this plus this is 0.5, all right? And that's the 0.5 that we had right here. There's our heads. For the 1, 2, 3, it's everything in this circle. It's everything in this circle, which is 0.75. So this is the 1, 2, 3. Well, when I look at this, look what happened to the intersection. It got colored twice. The reason it got colored twice is because it got counted twice. And because it got counted twice, it can only be counted once. So it got counted twice, once by the heads, once by the 1, 2, 3. So I needed to subtract it out once so that it was only counted once. So once again, it was colored twice, so it must have been counted twice. So I have to subtract it out so it's only counted once. All right, so let's put this all into actual problem where it starts to come together for us. So what's the probability of having a cat and a dog? I see the word and that makes me think intersection. So this is the probability of cat and dog, which is my intersection right here is 0.12. What's the probability of having a cat? So the probability of cat equals everything in the cat circle. So in this case, 0.18 plus 0.12 equals 0.30. What's the probability of having a dog? Well, the probability of having a dog is everything in the dog circle. All right? And so everything in the dog circle is 0.27 plus 0.12 equals 0.39. What's the probability of not having a cat? So every time I see a not, I know it's a 1 minus. So 1 minus whatever they were talking about. So 1 minus the probability of having a cat. So that equals 1 minus, and we said the probability of a cat was 0.3. So my answer is 0.70. What's the probability of not having a dog? Well, that's 1 minus the probability of whatever they're talking about, which in this case is a dog. So 1 minus the probability of a dog, which we said was 0.39, and that's 0.61. What's the probability of not having both? All right, a cat and a dog. So they're talking about both. Both is this. So 1 minus the probability of cat and dog. Because remember, this is also the intersection symbol. So 1 minus 0.12 equals 0.88. What is the probability of having neither a cat nor a dog? All right, so at this point, I can't have a cat or a dog. So this is going to be 1 minus the probability of a cat only, which is 0.18, plus the probability of both, plus the probability of a dog only, which in this case means my answer is 0.43. Pause for just a moment. All right, so the next thing it says, are having a cat and a dog independent events. And by the way, I'm not going to be able to put everything up on the screen, so you're going to have to follow along. Are having a cat or a dog independent events justify your answer? Well, if they're independent, we can use the multiplication rule. So that the multiplication rule said the probability of cat and dog equals the probability of cat times the probability of dog, because there's a probability of A and B equals the probability of A times the probability of B. Well, we know the probability of cat and dog, or both of them, is 0.12. The probability of cat is 0.30, and the probability of dog is 0.39. When I multiply 0.3 times 0.39, I get 0.117. So 0.12, 0.117. That is not a true statement. Because they're not equal, cat and dog are not independent events. So they're not independent events. That takes care of that one. The next thing says, what's the probability of having a cat or a dog? Well, because it has the word or, I know I'm using a union. All right. So a cat or dog, and that tells me I'm using the union symbol. So the probability of cat union dog equals the probability of cat plus the probability of dog minus the probability of cat and dog, or the intersection. All right. Well, the probability of a cat was 0.30. The probability of a dog is 0.39. And the intersection is 0.12. So when I subtract all that out, or add them up and subtract them, I find out the probability of having a cat or dog equals 0.57. Please do not forget that is the symbol for or. And that tells me that I'm using the general addition rule. All right. Next question is, what is the probability of having only a dog? The probability of having only a dog. Well, if I'm careful, I should be able to look and go, you know what? Probability of only a dog is just that probability right there. Probability of only a dog is 0.27. The next thing, complete the contingency table for the above situation. All right, so I'm going to redraw this real quickly. And when we do this, I had this labeled out like this. This is D for dog, not a dog. Cat, not a cat. And this needs to sum up to one whole. And this will always be one whole. All right. And I guess I made this a little bit too big. So there we go. That's a little bit better. All right. First off, I like to start with the intersection. Well, C and D is right here. So the probability of a cat and a dog is 0.12. The probability of having a dog but not a cat is 0.27. So this makes this 0.39. The probability of having a cat but not a dog is 0.18. And that makes sense because the probability of having a cat is 30%. And then we'll come back to that in just a second. The probability of having not a dog and no cat is 0.53, and that's what we calculated earlier. All right, that's what we calculated. Excuse me, this is not 0.53, this is 0.43. So this right here is 0.61. This plus this equals that. This plus this equals 0.7. This plus this equals 0.8. And notice all my rows and columns all add up. There's a 30% chance that we'd have a cat, a 39% chance we'd have a dog, a 12% chance we'd have a cat and dog, a 43% chance that we'd have neither, and I should have written that up there earlier when we calculated that, because we did calculate that up earlier. All right. And the nice thing about the table is it's going to help us with our next couple of problems. All right. The next problem says, given someone has a cat. So now we're looking at the cat column. And given is always in the denominator. And anytime you have a given, you're going to have an intersection on top of it. So given a cat, which is 0.30, what's the probability they have a dog? There's my intersection, and the reason I call that an intersection is because that's where it looks like they cross, like a street. So this is 0.12 over 0.3. All right? So that's one of them. The next one says, given the person has a dog. Oh, once again, they said given. Anytime you say given, it goes in the denominator, and there'll be an intersection on top. Dog happens to be 0.39. And it says, what's the probability they have a cat? Here's my cat. Where they intersect is 0.12. So 0.12 over 0.39. All right. Hopefully that's helpful. And that ends the notes on this section.